Okay, I think we're back, but it's going to take a second to show me that we actually are. Yeah, I really apologize for, I mean, I shouldn't have to apologize for technical difficulties because it's, the internet is outside my control because, who's my internet service provider? Spectrum Internet's terrible. And then OBS problems happen. When you guys listen to this later, I have flies coming out of my sink for no reason because I've cleaned everything in the apartment. There's no reason why flies should come out of the sink. You also notice that I'm sweating because the AC is not working right. So everything's just falling apart in my apartment. Okay. Let's see, is the video playback working yet? Let's just refresh this page. OBS said it reconnected. Okay, yeah, we're back. We're back. Okay, yeah, again, I'm sorry things are not working the way that they're supposed to. So this is where we were at. We had state A and state B. So state A was when the switch 1 was closed and switch 2 was open. State B, switch 1 is open and switch 2 is closed. And ultimately what we're trying to get at is what are the charges on these two capacitors. So in order to do that, that's really using this equation that we have here that we haven't really touched on this side of the equation very much. And that's to say that the negative time derivative of the charge in the box or in the surface that's parameterized by this integral of j dot ds, that negative time derivative of the charge that's in there is going to be 0. Which means that for the surface, and I can define some surface this way, so I'm getting the top plate here and the left plate here. The charge inside that surface is going to be a constant because the rate of change of the charge is not constant. The screen is still blurry. Hopefully that fixed it. It looks like the autofocus is working though. So the charge in this box is going to be a constant because the rate of change of it is equal to 0. And so this just says that there's some total charge inside this box. Okay. Now, this is the same box that we have here. So whether I'm in state A or state B, the total charge inside the box is going to be a constant. And so what that says is that I could find what the total charge in the box was here. That Q total is just going to be my Q1, my plus Q1 that I have here. This Q total here is going to be the same. Okay? Now, what changes is how the charges are distributed on the capacitors. And so I'm going to introduce a different Q1 here. I'm going to call this Q1 tilde and minus Q1 tilde. Now, this side over here is going to be a minus Q2 tilde and a plus, let me move my capacitor label down here. So this is C2, this is plus Q2 tilde. Okay? So now, because the total charge inside the box is going to be a constant, it says that the total charge inside here is equal to the total charge inside here. That says that plus Q1 is going to be equal to plus Q1 tilde minus Q2 tilde. Okay? Now let's look at this guy right here. This is going to be plus Q1 tilde because on this plate right here, I have the plus 1 Q1 tilde. And then right here, I have the minus Q2 tilde. So that's why for the second system, system B, this is going to be this right here. Okay? Now, in order to get a system of equations that I can solve, I can just draw two loops here. So one loop I could draw looks like this, and then this is the second loop. And as Brian pointed out previously, we have some choices for the loops that I draw. I could do the loop that goes around the outside. It's just a little bit redundant to do all three. It's any combination of those three loops. I just happen to choose the one that's in here and the one that's here. So if this is, I said there was some loop 1 here. Let's call this loop 2 and this loop 3. So loop 2, says that the integral over this loop of E dot dl is going to be equal to 0. And so this is going to say, going around here, my current, I didn't define the current. Let's say the current is just I going down. I'm going to have some minus I times R, some plus Q2 tilde divided by C2, and then plus Q1 tilde divided by C1 is equal to 0. Okay? The second loop, pretty simple. It only has two components here, so it's going to be, so this is loop 3. The integral around loop 3 is going to be E vector dot dl is equal to 0. This is going to give me a minus V2 plus I times R is equal to 0. And if I look at this system, I have one equation, two equations, three equations, and where's my fourth equation? Four equations. And my unknowns are Q1, Q1 tilde, Q2 tilde, and I. So I have four equations and four unknowns. Okay? And as always with these problems, count the number of unknowns that you have. You should have the same number of equations in the end so that you could solve them. And I'm not going to go through the process of solving this. If you did want to solve this, the way that you would do it is to say that, well, the first thing that I would do would be to find I. I is the easiest thing to find. I is just going to be V2 divided by R. And Q1 is already written in terms of V1 and C. So I could take this Q1 and plug it in here. And then I could solve this equation for Q1 tilde. And then plug it into this equation. Plug my I into this equation. Then this equation would only have a Q2 tilde. I could solve for that. And then I could take whatever I found Q2 tilde to be and then plug it back into this equation, and that would give me what Q1 tilde is. I imagine this question was not, this was a question that's just said find a system of equations that can be solved. It didn't explicitly ask you to solve it. Oh, this must have been a year that pissed Bassicus off. He actually did ask you to solve it. I wouldn't ask you to solve this. It's too much algebra. This is a physics test. It's not an algebra test. Okay, but the point, and like I don't even think I would ask something quite like this because I didn't talk about this as much. But the point is that you can define your loops, you can go around your loops, you can obtain your equations from the loops. And the other piece that, and why I said that this was a hard question and one that I probably wouldn't ask, is because what you need to do is you need to think about some box that I can define here where the charge inside that box is equal to a constant. And whether I'm in state A or state B, it's the same charge. And that's how I got this equation here. But ultimately, four equations, four unknowns, and it was this portion right here that was the hard part. But for me, things to learn for next time. If I talk more about this, it would be more fair for me to ask a question like this. But I wouldn't ask you guys one like this. Okay? So while I'm reading ahead and finding out what we're going to be doing next, go ahead and take a look at this and let me know if you have any questions. Okay. All right. So the next question is actually three questions in one. And you might say, well, that's not fair. You asked me three questions on a one question or on one page. But it turns out that these questions are all actually pretty straightforward. And they're easier variants of some of the circuits that we've had before. So the first one says, and I don't have the old chat, so I don't remember who asked the question, but somebody asked me something about determining the direction of currents and loops. So if you posted that question before, ask me it again so that I can make sure that I answer it. So the first circuit that we have here is going to look like this. R1, R1, and R2. R1, R1, R2, and these are both V. Okay. Okay. So here's an example of a year that didn't make Basicus angry, I guess, for this question. I wouldn't ask something this simple. And the reason why is there's only really one loop that you can draw here. So there's one loop, okay? And going around this loop, I needed to define some current here. So let's call this current capital I. This says, for this loop, integral of E dot dl is going to be equal to minus V. We have another minus V. I'm going to make this a minus 2V. And then this is going to be plus the current, because the loop is in the same direction as the current. And then I'm going to have plus I1 R1 plus I1 R1 plus I2 R2, which is really the same thing as plus 2 R1 plus R2 is equal to 0. And so what we end up seeing is that the current is going to be equal to V divided by 2 R1 plus R2. Okay. I realize I did that pretty quickly, but if you have any questions about how I combine this, I just didn't write out every term. I realized by looking at the loop that I could combine them like this. Okay, I can go back and explain that in more detail if that's confusing. Okay, the second one says we have, and it's times like this I'm really sad that I sat on my glasses because I can't see. This is R1. This is also R1. This is plus V. This is the same V. And then this is R2. Okay. So for this one, we can define some current I1, some current I2, and then this is going to be some current I3. Draw some junction, integral j dot ds over the closed surface is going to be equal to 0. And so this says this is equal to minus I1 minus I2 plus I3 is equal to 0. Okay. And then we can look at some loops. So I'm going to do this loop and this loop. Yeah, I mean, you might be seeing when I'm doing these, and there's not really any particular reason. I tend to draw the inside loops if I don't see a very good reason to go outside. I could have drawn this loop. You could do any one of the combinations of those, but the punchline is I need 3 equations because I have 3 unknowns. I don't know what any of the currents are. And so this is already 1 equation. I just need 2 more. So I'm just going to do this one and this one. Okay. So going around this loop, I end up seeing this is going to be plus I1 R1 minus I2 R2. This is going to be plus V. And so really this is integral, and let's call this loop 1 and loop 2. Integral for loop 1 of E dot dl is equal to this. This is going to be plus V, and then minus V is equal to 0. So the plus V comes from going across this one, so I see the plus first, and then I get to this one, I see the minus V. That cancels. Okay, we're still online. That's good. So then what we can do is we can look at, sorry, this should be an I2 R1. I2 R1. Then this one, this loop that I have here, so this is the integral around loop 2, says this is going to be equal to minus V plus I2 times R1, right? Coming around here, plus I3 times, what did I say this resistance was here? This is resistance R2. Is equal to 0. Okay, so from the equations that I have here, let's rearrange this. So this one says that I3 is equal to I1 plus I2. This one, when I rearrange it, says that I1 is equal to I2. And this one says that V is equal to I2 I2 times R1 plus I3 times R2, okay? So what I can do here is I can plug, let me think how I want to do this. Plug I2 in for I1 here. So that says that I3 is going to be equal to 2 times I2, okay? And now that I have this, I can plug it into this equation. So when I do that, V is going to be equal to I2 R1 plus 2 times I2 times R2. And so what this says then from this equation, now I'm making a mess of the way that I'm doing this, but I think you can follow the process if you're listening and seeing the lines that I'm drawing. This equation then says I can factor out an I2 from each one of these and divide everything else by the things that are multiplied by I2. And so that says that I2 is going to be equal to V divided by V divided by R1 plus 2 times R2. Okay? So that's what I2 is. And then I know that I1 is equal to I2 and that I3 is going to be 2 times I2. Okay? Okay. Yeah, Mark reposted his question. I'm still having trouble determining the sign of the current and the other components, V and C, and equating currents at a junction. Okay. Let me make up an example, and I'll come back to answer that question. Eric says, I know we can choose which direction the current can flow. Would it be wrong to have I2 flow in the opposite direction of what I've drawn? No. So you could have said, yeah, so what you're asking is, can I draw I2 going this way? You can absolutely do that. You can absolutely draw any one of these currents to go whatever direction you want. But what that's going to change is when I evaluate the loop. Say now I say I2 goes that way. When I evaluate loop 1, that's going to make this plus instead of minus, right? Because you see, if I go around loop 1, now the loop is in the same direction as the current if I redefine it going to the left. Something else that I noticed going around, was it today? No, it was, lose track of time. Today is Monday. Yeah, it was earlier today. Something I noticed going around earlier today was a lot of times when people ended up finding there was a negative sign somewhere in their answer, what they wanted to do is they come over here and they flip it. So they say, I'm going to make my current go the opposite direction as the way I drew it. Don't do that. Always define the current and then find what the current is here, whether it has a negative or a positive sign, and then just leave it the way that it is. Because if you do this and then flip it, you do this, you get an equation, it had a negative sign, now I'm going to flip it over here. You also have to flip the sign elsewhere where you did the calculation. And it's much better to just say, I got a negative sign over here. That just means that the current is going the opposite direction as the way that I drew it, and just leave it at that. Because you're artificially introducing an additional negative sign. If you flip this and then you don't fix what you had here. And who wants to go back through the calculation that they toiled over here and say, well, I found out when I did the calculation that the current wasn't the direction I drew it, so let me redraw it. What you really have to do if you redraw is you have to reevaluate what your loop equation says. Okay? So for this way now, this has a negative sign because of the way that I have it here and the way this loop is drawn. But in a very long-winded way to answer your question, Eric, you could define this whichever way you wanted, and then the sign comes out in when I go around the loop, is it in the same or the opposite direction as the current is going? Okay. So there was one more part to this, but I do want to come back to Mark's question because I think it's important, and maybe I think I might be able to answer it in this third part. And Mark, let me know if it's not a satisfactory answer. Okay. So third part here now introduces a capacitor. So probably didn't need to erase what I had there because it's really the same thing. It just has a capacitor there now instead of a resistor on the bottom. So this says I have this and then this. Like that. And V's are all the same still. So this is V, V, R1, R1, R2, and a capacitor. Okay. So now it's really the same process that we went through before, only now we have this capacitor here. So the first thing that I'm going to do is I'm going to put my charges on the capacitor. So this is going to be plus Q and minus Q. Now, as I was alluding to before, you're free to choose this however you want. I could have made this minus Q and made this plus Q. But there's a particular reason why I chose this to be plus Q and this to be minus Q. And it's because these are the positive sides of this is the positive end of the battery. And so if you have the positive end of the battery, what's really going to happen is it's going to put a positive charge here. That was something I kind of swept under the rug, but like I said, you can choose it however you want, and then the real thing that's going to happen here is that if these are positive, this is positive. But it's not always easy to see that that's what the case is going to be. Say these had two different voltages and then this one was flipped. Then you wouldn't be able to say whether this was positive or negative here without knowing the relative magnitudes of the voltages for the two batteries. But here, you know, because this is plus, this has to be plus. But define it and then do your loops. You'll still get the same answer. Okay. So the second thing that I need to do is I need to define some current. So let's call this some current I1, call this some current I2, and then we could say that there's some current I3 here as well. So draw my box. This says sum I in is equal to sum I out, which says that this is going to be I1 plus I2, which is going to be equal to I3. But we know that because there's a capacitor down here, if this is fully charged, I3 is actually 0. So I3 is 0, which says that I1 is equal to minus I2. Okay? Now, let's do some loops here. So again, I'm going to pick the inside loops. So call this loop 1 and loop 2. So the integral around loop 1 of E dot dl is going to be equal to minus V plus I1 times R1 minus I2 R1 plus V is going to be equal to 0. So my V's are going to cancel. And I see something kind of peculiar here, because from this equation, what it says, I can cancel my R1s as well. This says that I1 is equal to I2. This one says I1 is equal to minus I2. There's only one very specific set of circumstances where this can be true and this is true. So think about it like in terms of numbers. If you want to think there are numbers that can evaluate for I1 and I2. When can the number 4 be equal to negative 4? Right? Because this says this number is equal to that number. This says this number is equal to the negative of that number. 4 is never equal to minus 4. But there is one very particular set of circumstances that does satisfy this equation, and that's when I1 is equal to 0 and I2 is equal to 0. Because 0 is equal to 0, 0 is equal to negative 0. So I1 is equal to 0. And that's also equal to I2. Okay. So now let's look at loop 2. So for loop 2, integral E dot dl is going to be equal to 0. This says minus v. We already said I2 is 0 because I1 is 0. And then this is going to be plus Q divided by C. There's no current in R2. That's equal to 0. Q is equal to V times C. Okay? And that's it. Okay. So, I'm still having trouble determining the sign of the current and the other components, V and C, and equating the currents at a junction. Okay, yeah. So now let me kind of lay out all of the rules so that hopefully I'm answering Mark's question. So it's really the whole thing that I need to lay out here. So when I do the integral of E dot dl over some closed loop, this is equal to 0. But the question is, if I go over some resistor of integral E dot dl, this is either equal to plus or minus I times R, right? Same thing with the capacitor, same thing with the battery, right? So integral over the capacitor of E dot dl is either going to be plus or minus Q over C. And integral over the battery of E dot dl is either going to be plus or minus V, okay? The real question is, when is this positive, when is it negative, when is this positive, when is this negative, when is that positive, when is this negative, okay? So let me just kind of make up an example here so we can see all three cases, and then I'll talk about the junction. So this example, simplest thing I can think of right now, is going to be this, okay? So I have a battery, I have a resistor, I have a capacitor. This has the same size. No, I made it too big. Okay, but this is capacitor. So this is R, this is C, this is V. Okay. So as always, what we need to do is we need to label some things. I'm going to label my current going up. I'm going to label this to be minus Q and make this plus Q. Okay. It doesn't really matter, but you'll see what my point is here. So now let's draw some loops. So we have some loop 1 and some loop 2. Now to go to who was it? I think it was Brian. Was asking me about outside loops. This is a situation I would do an outside loop. And the reason why I'm doing an outside loop here is because if I do the inside loop, I'm going to have this Q in terms of an I, when it's easier to evaluate if I have the Q in terms of a V. We'll see this when I go through this. So let's first look at the integral over loop 1. And that's really getting at why is this plus or why is it minus. So for loop 1, when I go across the battery, do I see a negative or do I see a positive with the direction that I'm going around the loop? So if I'm going around the loop this way, I'm going to see the negative. So that's why this is negative. So for this clockwise loop, I see the negative. But if I did a counterclockwise loop, this is going to give me a positive. So that's where this plus or minus comes from. And it's similar to this one. It's a matter of, as I'm going around the loop, as I'm walking around this part of the circuit, do I see a negative or do I see a positive? For the way that I defined it here, I see a negative. So I see the negative terminal of the battery first. So that's going to be minus V. Now let's talk about this one right here. So when is the current going to be positive or negative? So in this case, as I'm going around this loop, I define the current going through the battery to be up. But the loop is going to be going down when it goes through this resistor. And so what that says is this is going to be minus IR. Okay? So again, this is minus IR because the loop is going the opposite direction as the current. If it's going the same direction, had I chosen my current to be pointing down, then this would be positive IR. And then this is equal to 0. Okay? So ultimately what I ended up seeing here, it's kind of interesting. When I solve for I, V is going to be equal to minus IR, or I is going to be equal to minus V divided by R. I'm getting a negative current here, which is kind of interesting when we think about it, because why would the current be negative? That actually just means that the current is going to go the opposite direction as the way that I drew it. And so I drew this current going up. Because I'm seeing this as minus V divided by R, that really means that the current is going to be going down. And again, that follows some intuition that we have, because the current is going to point in the same direction as the electric field. And the electric field is going to point from positive to negative. So that says the current really should be going this way. But I had defined it going the opposite way, which is why when I solve for the current for my loop equation, I end up seeing this as a minus V divided by R. Okay. So now let's look at the second loop, and that's going to get into this guy. Okay. Second loop says, going around, I see a minus V. So this is integral E dot dl for loop 2 is going to be equal to minus V. And now I'm coming over here, I see a plus Q. So when I see a plus Q, I write plus Q over C. And then I get back to the bottom of my loop here, so this is equal to 0. So this one says that Q is equal to VC when I solve this equation that I have here. Okay. So the punchline is, for when I do the loops and I'm breaking it apart, and when I'm going across a capacitor, or when I'm going across a battery, the contribution is going to be positive if, as I'm going around the loop, the first thing I see is a positive. It's going to be negative when I go around the loop and the first thing I see is a negative. Okay? So I could have done this loop going the other way. And if I had done the loop going the other way, what I would see is this is minus Q divided by C. And then this is going to be plus V. Again, because I go around the loop, I see a minus Q. Keep going around the loop, I see a plus V. That's equal to 0. And really, this is the important thing about this. It shouldn't matter how you make your choice, right? The physics should be the same regardless, right? This equation is actually just the same as this equation. Okay. Now the other part of Mark's question had to do with the sign of currents and equating currents at junctions. Okay, so equating currents at junctions, I'm sweeping a little bit under the rug here, and I'm presenting it in terms of the most general formula. So that's to say that the integral of J dot ds is equal to minus dq dt, which is equal to 0. This is the most general way that you can do this. And I have kind of a penchant for doing this, because rather than strapping you with a whole bunch of different equations, I personally think it's better to write a general equation and understand what it means. And I think I didn't explain what this means as well as I could have. And why this actually reduces to this. So and this is noticing the errors of my ways. I out. For us in this class, just do the sum of the currents in is equal to the sum of the currents out. I need to, and this will go part of into the writing that I'm going to be doing after the end of the semester to polish this. Really, what this flux equation says is that consider some box, and this is the same thing as we had when we did Gauss's law, when we were talking about boxes. Anything that goes into this box is going to be negative, because the ds vector always points out. So if you're going into the box, let's say like on this face right here, if I'm going into this box, the dot product is going to be negative because going in is this way, the face of the surface is this way. I get a negative sign. If I'm going out of the box, I'm going to get something positive, because going out of the box is the same direction as what's perpendicular to the face pointing outwards. Ultimately, that's going to reduce to just this equation here. So if I have some junction, and I can make this up as however I want, call this I1, call this I2, call this I3. What's going into the junction? I3 and I1 are going into the junction. So this is I1 plus I3. What's going out of the junction? I2. So this is just equal to I2. It ultimately gets at the same thing, and really, I didn't realize this until now when I'm thinking about why it's good to do this in general, why it's good to write the equation like this. It's because of this term. This term allows me to say something about, if I have two capacitors in series, why is it that if this is C1, this is C2, I can label this as plus Q1 minus Q1 plus Q2 minus Q2. Why is it that Q1 is equal to Q2? This equation does both things. It explains both how junctions work for currents, as well as how capacitors share charge. That's really the reason for having this, because you can put both of those ideas into one equation. And to you guys, that might not mean a lot, but it's always better. And this is something that you do in physics at higher levels. It's always better to write things in general rather than writing a whole list of equations that are true sometimes, but need conditions for them to be true. You encapsulate more information writing things succinctly, and ultimately this equation means more because it has more applications to it. Again, that's not particularly satisfying. I need to think about. I need to think about some questions, and there are some questions that I could ask about this. We could have, honestly, if I had thought about it more, it's going to cut out some things that we might do at the end of the semester. I probably could have given 2 days to just this equation to make you think about it, because what this equation says is something that's really interesting and something that is intuitive on some level, because the current density and the charge are related to each other. The current density says something about how charges are moving, and the charge here just says how much charge do I have just sitting there. And so what this equation really says, even if this isn't equal to 0, you can generalize this even more and say it's not equal to 0, that whatever charge I have leaving an area is going to tell me how the charge is depleting on the inside. That's really what this equation says. So charges leaving an area tells me how much charge is decreasing inside the area that I had it in. Okay. Again, and this is part of a little bit of a problem for me when I'm trying to think about how I want to bridge this. So part of what I'm doing in writing this course material and writing these problems for you guys to work on is to bridge the freshman level physics or the introductory level physics for physics majors. Physics majors see actually, in a way, what a lot of you are seeing right now getting into the upper level engineering classes is that there's a big step up for how difficult the material is. And part of what I'm trying to do is I'm trying to write the calculus and the physics in a way that's approachable at the level that you're at, that prepares you better for your upper level classes. I think I've been moderately successful with some of that. Not entirely successful, but this equation, for those of you that are taking fluid mechanics, it says the same kind of thing in the language of fluids. So that's to say, if I have some amount of water that can be parameterized by just the amount of water. So here it's an amount of charge, but we can think about like water instead of charge. The rate of change of the water that I have in some area is going to be related to the amount of water that's leaving that area. That's really what this equation tells you. And why I think it's important, and why I think I need to do a better job explaining this equation in particular for you guys, because again, I want this to be a stepping stone for physics majors. But for engineers, this concept of how do I write, how much stuff do I have in an area versus how much I have leaving in the area in an equation like this is really important. This gets into, for those of you doing the fluid mechanics, this gets into Navier-Stokes. It's going to be related to Bernoulli's equation. A lot of the physics that I'm doing here and the formalism that I'm using for the calculus carries over to the more advanced engineering classes, which again is kind of why I'm trying to do it the way that I'm doing it. I'm sorry if that's a really long-winded, ranchy kind of explanation. Okay. Eric says, can you explain the switch problem? More specific, what's going on with the boxes and the tilde? Okay, yeah, let me come back to that, because again, that's all about this equation right here. It's all about that equation. So let me just do the whole thing over again. So yeah, because it got cut off in the middle, and I hopefully it doesn't happen again. So really, we have two states for this problem. I'm not gonna draw the general switches open, switches closed. I'm just gonna draw it in the two states. So the first state looks like this. I think this was a V1. Yeah, this was a V1. This is a V2. This is a C1. This is a C2. And this is a R. Okay. So again, this is really important to you guys that are doing fluid mechanics. What I'm ultimately doing here is I'm saying that there is some box, and inside this box, there's going to be a total amount of charge that's going to be constant. Because for the very specific case that we're looking at here, this equation is equal to 0. So if I have minus dq dt is equal to 0, what does that say about q? Well, if I have a derivative of any function, I can draw some functions. I can draw a function like that. I can draw a function like this. This function has a different derivative at every point, right? The derivative is just going to be the slope. But if at all points this derivative is equal to 0, as in this case, then what that says is the value of q is just a constant, right? So if this was 4, right? So say this is, if I want to make this position versus time. This is actually a very boring thing that's happening here if we think about like the physics of what's going on here. If I'm plotting x as a function of time, and dx dt is equal to 0, that just says that something, it just stays in one spot. It just here, it never moves, nothing happens with it. It's just at a distance 4 meters, let's say. Okay? It just sits there. So for this equation, what this says is that Q is equal to a constant. And that's true whether I have the first case where I have this switch closed and this switch open, or I have the second case where this switch is open and this switch is closed. Q inside the box is just a constant. So draw my box again. Q in this box is a constant. Q in that box is a constant. And I'm just going to call the Q in that box Q total. Okay? I could call it whatever I want. And the reason why I'm calling it Q total will probably make a little bit more sense in a moment. But it's just some constant. And in this box, it's Q total. In this box, it's Q total. Now, this is where I'm getting into the Q, Q1 and Q2 tilde. So for this situation, I'm going to say that there's some plus Q1 here and some minus Q1 here. Nothing's going to happen with this capacitor. It's not connected to anything. It's connected on this side, but in order for there to be charge to accumulate on this, I need to close this, and then charge can flow through this whole line here. But if it's broken, nothing can flow around here. So any charge that I have here has to be 0. Okay? So now I can ask myself, what is Q total inside this box? Well, Q total inside this box is going to be plus Q1 plus 0. So that says Q total is going to be equal to plus Q1. Okay? Now I can do the same thing here, and this is where notation is a little bit weird. Why am I putting tildes over the top of these? Q in the box has to be a constant, but nothing says that I have to keep the same charge here as I have here. And in fact, if imagine I had this plus Q here. So imagine I just had this situation. So this is just what's happening in the box. And I had some plus Q1 here. What's going to happen when I close this switch? These charges are going to repel each other. And so because they repel each other, they're going to reorganize themselves on these two plates. The plus Q's don't want to be near each other. The only reason why I had that plus Q1 here at all was because I had the minus Q that's outside the box here. That's forcing this plus Q to be here. But if I close this, so I had the switch open, now I close it, now this plus Q1 can say, hey, I don't want to be over here by those other plus Q1s. I want to be a little bit over here and a little bit over here. So I can be as far away from the other plus Q1s as possible. Charges are very antisocial. They don't like other charges. They try to move away from them, right? So because I close the switch here, these charges can rearrange themselves. And closing the switch has another property that's going to be important here. It allows me to change what the charge is on this one due to some external electric potential that I have in terms of the battery here. So the reason why ultimately I'm calling this a plus Q1 tilde and a minus Q2 tilde, plus Q2 tilde over here, minus Q1 tilde, is because this is still a charge on the capacitor C1. That's why I have the 1s here. That's what this is. So Q1 goes to C1. Q1 tilde has to do with C1, but it's not going to be the same as Q1. It's going to be different. These are going to rearrange themselves when I close this switch. But the charge inside the box has to be a constant, right? Q total is just a constant. So what that says is, now I rearrange these charges. I have this plus Q1 tilde here and this minus Q2 tilde. This just says that Q total is just going to be the sum of the charge in the box, right? So this is going to be plus Q1 tilde minus Q2 tilde. And because the Q totals are the same across this system to this system, this says that this is just going to be Q1. So that's where this came from. Okay. So hopefully that wasn't. I did go on. I did go on a rant about this guy for a while, but I do think it's really important. And again, what I'm trying to do for you guys is to give you more exposure to how calculus comes into, in my case, and what I'm teaching, how calculus comes into the physics, because it's going to be really important for you to see how the calculus comes into the engineering later. And so if the first time you see fairly advanced applications of calculus is in an advanced engineering class, it's going to be difficult for you. So again, in doing this, there's a lot of nice symmetries I can play around with in physics. I can do things in terms of spheres and cylinders. So I'm introducing the concept of the calculus without having difficult calculations, so that hopefully when you're seeing these types of arguments with more difficult calculations, you'll be able to do them with more confidence as you're moving into your upper division classes. Okay. So I'm using the different states to solve and define Q total in the box that's made up from the junction of the switches. Exactly. So the two states, Q total is the same in the states, but saying what Q total is different in the two states. So these as a value, these Q totals are going to have the same value, but how they're distributed is going to change in the two states, and that's really the game that I'm playing here. Yeah. And this makes me think man, I wish I could teach you guys physics for 4 semesters. I can't nearly adequately do all of the things that I want to do in just one when I'm just thinking about electrodynamics. This is an incredibly important equation, and one that I don't have the time to adequately do it justice. But hopefully the things that you guys are walking away from this course with are what do equations of this form mean? What do equations of this form mean? We've seen both of these already. So this one is kind of like Gauss's law, which is also like this equation. This equation is like the way that we're doing circuits, integral E dot dl. So it's thinking about adding up pieces going around a loop. This is thinking about adding pieces that are going out of some closed surface. These are really the basis for Maxwell's equations, because you think about all the different combinations of how I can do E dot dl, B dot dl, because B is going to be a magnetic field, E dot ds, B dot ds. That is Maxwell's equations. Those are Maxwell's equations when you think about what all those combinations are and then what the right-hand side of the equation is going to look like. And again, for your engineering classes, this equation right here is the first law of thermodynamics for when this is equal to the work. And first law of thermodynamics isn't over a closed loop. But first law of thermodynamics can be formulated in terms of integral of F dot dl is equal to 0. But when you're talking about heat added to a system, work done by the system, some force that can be exerted on or by the system, that's something like this. Your fluid mechanics, Navier-Stokes, comes from an equation like this. Typically, it's written in the differential form, but it's still thinking about some field that's leaving some closed surface. Bernoulli's equation. Bernoulli's equation comes from this guy. What else? Circuits we're already seeing, so that's another application. And you could be creative. There are things that I'm probably not thinking of that come from these equations that you'll see as applications in your engineering class. Okay. So I think I've ranted at you guys enough about you know, my particular outlook when it comes to teaching this course and why I think it's going to be useful for you guys in the future. Let me know in the last 30 seconds or so if there are any other questions that you guys have. I'll answer those, and if there aren't any, then that'll be it. And hopefully Wednesday I don't have the same technical difficulties that I had today. Jeez, hopefully I can get my AC fixed. It's terrible in here right now. All right, so I'll see you guys tomorrow. We're going to be doing more circuits in recitation. So hopefully what you guys are seeing as the course progresses is that things are kind of hard when you start. I don't expect you to know them outright, but you guys have been working really hard. I've been really pleased with your work ethic, and it's at the level that you can do things. You just need to work some problems and ask me some questions as we're going. Okay, so that's going to be it. I'll see you guys tomorrow.